Hello, everyone. Today, now that we've introduced some of the work with functions of multiple variables, right? Functions f that depend on two or more variables, f of x, y, or later f of x, y, z even, okay? And in discussions, we can do work with taking the limits of those functions, right? As a point in our domain, x, y, approaches a particular point, finding that limit, right? So those definitions for the derivative can extend in that format and discussion as well. Okay, so let's start to discuss then what some of these derivatives look like. Let me share my screen or share the document camera. All right, and so now we can start to work on our discussion with what we call partial derivatives. Okay, and so with this going, try to make sure this is clear, right? So for functions, of several, right, more than one variables, like our f of x, y, or g of x, y, and z, when we take a derivative, we must be clear in our notation, in our discussion, what variable we are taking the derivative with respect to. Okay, right? So again, thinking back with our Calc 1 or that Math 20A here at MPC, right? Notation, we're talking about, okay, maybe I'm taking my function and taking my derivative with respect to x, or likewise, maybe I'm taking the derivative with respect to t, pardon me, for a function, right? Maybe we're taking like the derivative of the velocity or something like that, okay? But if we have our function, and then what variable, right, is our independent variable, what variable we're taking the derivative with respect to, okay? But now, when we have functions of multiple variables, we have to be a little more clear, and our notation is going to change slightly so that we can be clear on what variable we're taking the derivative with respect to, okay? So now, for our kind of Calc 3, our third semester calculus, Math 20C here at MPC, okay? We consider taking the derivative with respect to just one variable at a time. And a kind of key idea in this process is that we hold the other variable involved, or possibly variables if there's more than, right, more than just two variables, right? We're going to let one be variable, let one change, and hold the others to be constants. Okay? And so some notation here. We're going to start talking about our partial derivatives. And if we have our function that can depend on multiple variables, f of x, y, and z, I'll do 3 variables to start in the notation, but again, we'll scale it back. Most likely our functions will just depend on 2 variables. But what we can start to look at is taking the partial, and now with that partial derivative notation, instead of that kind of standard English or straight d, now we kind of have our more script-like, right, our curly d dx for that function of x, y, and z. Okay, and so notation we can call like df dx, and so having that kind of curly d identifies as notation-wise when we see that okay, it's just a partial derivative, that there's other variables that this function f depends on, and we're just taking the derivative, considering x to be variable changing. All the other variables that may appear are to be considered constants, right? Or another notation here, f with a subscript x. So that's our partial derivative of that function f with respect to x variable. And we can look at those others involved, right? Taking our picture, sorry, there should be a y here. Taking the partial of that function f of x, y, z with respect to y now, df dy, or f sub y. And then lastly, taking a derivative with respect to z, or whatever other variables may appear, f sub z there. Let me fill in my function we're taking the derivative of. And there's our notations, okay? Those subscripts, or that curly d notation. This identifies that we're taking the derivative of this function, f of x, y, z, with respect to one particular variable, okay? And so when we go through this process, looking at those, okay, the partial derivatives follow the same type of limit definition of the derivative that we saw in Calc 1, right, Math 20A and NBC. So again, 20A, Calc 1, we saw that df dx, right, f prime, that was equal to the limit as h goes to 0 of f of x plus h minus f of x all over h, right? So a function f that just depended on one variable x, right? That difference quotient, letting x change slightly between x and x plus h. Let that difference between those two variables, those two quantities, shrink down to 0, and that would give us our derivative, right? So now, with our partial derivative discussion, Math 20C here, when we have, let's bring in, right, this capital F of xy, just two variables, okay? Slide this up slightly. And again, 3 variables, 4 variables even, the similar discussion. Now, when we take the partial of that function with respect to x, broadening my notation here. The limit notation says we're going to take this limit as h goes to 0. And now for our difference quotient, notice what happens. We're going to have here our function f, and now we're going to let x be the variable that we're going to find that difference quotient by. We're going to let vary. So I'm going to put here x plus h. The other variable, y, stays the same. Minus f of x, and then y, still the same. Okay? And that's all over h. So in this discussion, notice x is varying, right? We're looking at that changing values there. Y stays the same. Whatever value for y won't plug in later, we can do so. Okay? So that's the idea that I mentioned, keeping one variable constant, the same, and let the other variable vary, right? Change, and see and mark that rate of change. And so then, in a similar way, dy of that function, f of xy, if we have that function again, now we can look at the partial with respect to y. So then, in this case, my x stays the same, and it's the y variable that we're going to alter, that we're going to let shift. Okay, that direction red, y all over h. And just to finish out, right, this is our f sub x, f sub y. So there's that limit discussion, right? We're not really going to resort to using that limit notation or that limit definition for finding the partial derivatives. But if ever we're stuck or kind of build on more complicated information, we can go back to these statements to prove, to verify, to work through certain problems. But more often than not, we're going to see our typical kind of differentiation rules, and we're going to work through these functions of multiple variables and find these different partial derivatives. Okay? And so in that view, right, graphically, visually, on our surface, where z is given by that function f of xy, or later function of 3 variables, so on, okay? On our surface, that partial derivative represents that rate of change, that slope, across the surface following a path where, again, either x or y is held constant. And depending on which x or y value you want, right, we can plug in any value. We're going to get some expression for that partial derivative. And we can plug that particular value for y in. So along that stretch where y is equal to a certain number, and then for along that way, for those different x's that show up, we can plug in that value, right? So again, I know that's a little bit stretched in our thinking. Let's put this picture up, and hopefully this can support. And again, the textbook has probably more elaborate, clearer pictures than I can draw here. But let's go through this process, right? So as we go through, right, let's consider that we have this surface here. And again, my generic one like this sheet of paper folded across, right? So we have this surface for any xy in the domain. We can send it up to our function here. Just send it to our function, get that z coordinate, right? So when I look at my z sub x, or df dx, right, or f sub x, looking at these different notations, taking the derivative of that function with respect to x. In that notation, that means that y is constant, and we're looking for that rate of change, that slope, in the x direction. Okay? So again, with our view three-dimensionally, it can be a little bit troublesome as we start, but hopefully never impossible, right? So in looking at this work, I'm going to hold y constant, right? So for some value of y, right, along that path, on our curve, on our surface here, right, this is that path where that y value is the same, right? So taking those points, projecting them, sending them through our function, we're getting here. And I don't want to get too jumbled in my graph, right? So I'm looking at all those points where we have a fixed y value. And then whatever this expression is, right, some polynomial, some trig function, whatever it might be, right, I can plug in any x value, that particular y value for that path, and then my rate of change, right, so my kind of slope, we can come back to our vector value function, right, this tangent vector, what direction we're moving there, right? This is giving us kind of that rate of change, whether we're going upwards, downwards, how rapidly x is changing. So if we get like a negative, right, that means x is decreasing, we're going downwards. If we're going this way, right, we're climbing, x is increasing as we walk along this path. And we'll get into some of our directional derivatives later in this chapter or the next as well, right? Because instead of having just to be fixed in just how we're changing the x direction or solely the y direction, maybe we're pointing somewhere else. But again, I don't want to get ahead of myself. But we're just kind of looking at that. If we were walking along that surface at one fixed y value, walking on this path, that derivative, that slope, tells me, okay, what we're experiencing in that x direction. Positive means, right, we're increasing, we're going upwards. Negative or decreasing, x is going downwards, right? And we can start to put that into play, like when we're looking at, right, with the topography maps that we talked about with our introduction to those functions of several variables, all those level curves, right? We kind of started to see, okay, if I was to walk away, what direction, how am I changing that x direction, how steep of a slant are we going, that idea, okay? And again, not to jumble, but we can think again, if I was taking the derivative with respect to y, x is going to be constant, and we're kind of measuring at any point along that x value what the slope would be, what that rate of change would be in the y direction. And depending on our expression, right, we can plug in any different y value, any different x value, and get at that particular location, that particular point on our surface, what that slope would be. Okay? All right. So with that said, let's go through the work. Okay? So for examples here, let's say we're given the function f of xy is equal to 4x squared, y to the third, minus 9x plus cosine y. Okay? So there's our function of several variables, x and y in particular. Okay? So now, let's find the following partial derivatives. All right, so part A, let's look at f sub x, right? The partial of f with respect to x. So if I'm going to take that partial with respect to x for my function, sorry, curly d, not regular d. Plug in our function here. All right. So in that process here, in the notation, we're kind of identifying, okay, that x is the variable. Any other variable is just going to be a constant. So y is a constant. So just like back in 20A was a little bit tricky to work on, but something we kind of started to build up in that notation wise, right? Like seeing that symbol pi. It looks like a symbol. It's not a number. It's not 2. It's not 5. Pi is just a constant. So we just carry it around with us, that coefficient, that constant. So now that's how y is acting, right? So even this y cubed, even though it's multiplying that x squared, is just a constant, right? So off to the side here, thinking about like that 4x squared y cubed, x squared, there's my variable. That's the one that's going to actually get the derivative work done on it. That y cubed is just a constant, right? So this might be like similar to having like 4x squared times pi, right? And we can rearrange, make it 4 pi times x squared. And then we can go through our derivatives, right? Similar to this cosine y, that entire component, that's all constant in view of taking the partial with respect to x, right? So coming down a little bit, that partial with respect to x, let's bring back my derivative, partial derivative notation real quick here. Give myself a little bit more space, make sure I write more legibly. So as we take that derivative, that partial derivative of f with respect to x, work on these pieces, right? So again, those constants remain. The derivative of that x squared, 2x, right? Our typical power rule that we'd have to follow. Right? My subtraction will come down. The 9x, there's 9. Right? X at first goes away. And now in this case, that's going to be 0. That's just a constant in the view of taking the partial with respect to x. That's just a constant. So that's going to be 0. Right? Just like a pi. Cosine of 1 is just going to be 0. So in the end, that partial, simplifying here, 2 times 4, pardon me, is 8xy cubed minus that 9. There we go. Zoom out a little bit there. Okay. See my original function. Right, there is some kind of interaction between the x and the y in that term for the original function, but when I take that partial derivative with respect to x, that y cubed in the view of the partial derivative with respect to x is just a constant, just like a pi. That's what I always go back to. So those coefficients, those constants come out, derivative, our power rule. When it comes to that x, anything that's y, constant, either we're going to carry it with part of the coefficient or taking derivative just a constant term, 0. All right, so let's see what this expression compares. If we're taking the partial with respect to y, right? So taking the partial of our function f of xy with respect to the y variable. Give myself some space to write here. Similar to what we saw when we were taking the partial with respect to x. Now, y is variable. Y is the independent variable we're considering. X is going to be a constant, right? So slide this up. So in this case here, that's just a constant coefficient. There's going to be our variable term. The 9x minus 9x, that's all constant. No y's there. And then lastly, that's going to be our variable. We're going to be able to use our typical differentiation rules. Just keep track. We're taking the respect to y, right? So going through it, right, that becomes our f sub y equals, let me rewrite my notation real briefly, y, sorry. I know we get in that habit. We're so used to putting d dx that we start to unconsciously just go into habit and write it. Taking time here to be more careful. All right, so here we go. So for our f sub y, now the constant comes down, 4x squared. Our power rule for the y cubed, 3y squared. This constant, so minus 0 or plus 0. And now there's just our regular trig. We're going to get derivative cosine, negative sine of that independent variable y. So in this case, be careful, it's not an implicit differentiation. Y doesn't depend on x at all. In the future, we'll see that kind of chain rule, that kind of work where maybe this variable y depends on another variable. But in this instance, in this notation, our function has two independent variables, x and y. Y doesn't depend on x at all. So we don't have to do that chain rule. We don't have to do the implicit differentiation involved at all. Okay. So just simplifying this down, I'll slide that paper up, zoom out a little bit just so we can see that comparison that we're not going to get the same expression. We're going to get here 12x squared y squared minus the sine of y. So notice, our partial derivatives aren't identical. We're getting two different expressions. So if we were to graph that, we can try it on Desmos graphing or whatever, GeoGebra, whatever graphing tool you may find useful. And again, we're thinking for any x and y value, we can plug in, and that partial derivative is going to give us that slope, that rate of change in either the x direction or y direction, depending on whatever x and y value we plug in. That particular point from our domain, sending it through to our function. At that location, we get that slope. Okay. All right. And so we'll do another example, of course, but something else I wanted to bring in, right, before I forget to mention it, we can continue to find to evaluate higher order partial derivatives as well. Okay, zoom in here. So again, considering if we're given a function, capital F of x, y, or later f of x, y, and z, right? We can take our partial with respect to x, get that result, right? That df dx, or f sub x. So there's my first partial. With respect to x. But just like we would have done back in 20a, we can take the partial of that partial derivative, right? Or here, the partial derivative of the partial derivative of f with respect to x. So looking at that notation, d squared f over dx squared. So notice how the dx is kind of get stacked, get combined. But in my notation here is d, only the d is being squared. F is the single function we're taking the derivative of. Or in this case, f sub x, x. So there's our second partial with respect to x. Partial derivative, I guess, is to say more formally, but we get lazy and say it's our partial to represent partial derivative. Okay. But we get that notation, and we can go at a third time, a fourth time, f sub x, 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 right? We can continue that process. And then likewise, with respect to y, jumping to my notation, all right, we can take our partial with respect to y, then taking the partial derivative again with respect to y of that result, let me put it that way, where we're going to get d squared f over dy squared, or I don't necessarily need the parentheses. More common, we don't. Okay, but here we're getting our f sub y. So there's our second partial with respect to y. Right? So we can find the first derivative, second derivative with respect to the same variable. But of course, that note comes in. We can take those derivatives with respect to either variable as we go forward. So we kind of call here our mixed partials. Right, so we can start off, maybe we're going to take the derivative with respect to x for our function. Right? Get our df dx, or your f sub x. And then maybe after that, what if I take my derivative with respect to y for that result? Right, so taking my partial with respect to x first, and then taking the derivative with respect to y, the partial derivative with respect to y after that. In our notation, we're going to get here, right? And again, looking at that process, right? D squared f dy dx, right? Or more commonly, what we start to see is that function f. And then going in order, I did my x derivative first, y derivative second, right? So our subscripts in order, the closest one, right? The first one we see, that's the first derivative we did. Outer later in the sequence, that's the second derivative we did. And so if instead we had taken that partial of f with respect to y first, right, getting that f sub y to begin with, then taking the derivative with respect to x after that, in our notation, now we're going to get that d squared f dx dy, or again, the notation we're going to see more often, that's subscript notation f, the first derivative took y, second derivative x. All right, so we're mixing the variables instead of having all x's or all y's. So there's our mixed partial derivatives, right, to get this second result. Okay. So one last common example. All right. We'll kind of go through some practice here and showing as well. Is that when we start to look at some of the expressions, right? So in our process, given a function f of xy defined over a region D containing the point AB, right? So we have some function defined, right? Hopefully continuous over some region containing this particular plane inside. Now, if both the partial with respect to f, or if xy, partial of f with respect to xy, and the partial yx, right, those mixed partials, if those are both continuous over that region, that disk D, then when we look at the results of computing those partials at that particular point, they're going to be equal. And so for a lot of functions that we'll see, when we have continuous, right, expressions where we can evaluate it, we don't get zeros in the denominator, asymptotes, taking squares and negatives, so on. But many functions that we work with will have equal, right, or identical mixed partials. Right? So no matter which order you take the derivatives with respect to, x first and y first and x, those results for many of the functions, not always, right, has to kind of make sure that those expressions are continuous, but they're going to be equal. And most times, right, equal means identical for us. And this discussion, this is Clairaut's theorem. And again, I'm probably mispronouncing that name, so my apologies. Clairaut theorem, Clairaut's theorem, okay, from our text. All right. And so as we go through, we can look at some of the expressions. Maybe I'll write these up and include them in notes, just so this lecture is not too long. You can check those out. I'll work on some of those functions, take their partials, and I'll put that on our site for review. Okay? All right, I'll leave that here. If you have any discussions, questions about that lecture, please let me know. All right, take care.